Uh, hey everyone, welcome to this ZNotes live academic session. Today we're going to be doing physics, and we have published author Kaleem Akbar with us here today. We're going to talk about gas laws, and particularly today we're going to solve past paper questions. And without further ado, let's get started.
Thank you very much again for the introduction, Pugs. ZNotes, it's nice to be back again. Yes, today we are going to go through a few gas laws questions that are mixed in with some other topics, as is normal for any examination paper. So let's get stuck right in. So question number 4, which comes from the May-June 2016 paper 4 variant 3. In an industrial process, a gas that is already at high pressure is trapped in a large cylinder by a piston. Figure 4.1 shows the gas, the cylinder, and the piston. Now, guys, that's a bit like this piston right here. Okay, so if I was to seal one end of this piston with my thumb, here is my gas, and I could create a very high pressure by squeezing this in. So the piston is pushed into the cylinder. As the pressure of the gas changes, its temperature remains constant. Now, that is a humongous hint towards Boyle's law. P1 V1 equals P2 V2. If you remember from the lessons, the idea in any experiment is not to change more than one variable at a time. Okay, you do that because when we did the lesson, we realized that volume, temperature, and the mass of gas all had an effect on pressure. I mean, look, this is like a little toy bicycle pump. But if you've ever used a bicycle pump, or a pump if you like, if you've ever used a bicycle pump to pump up a football, a basketball, a netball, the tire of your bicycle, you move that in and out quickly. Anybody that's ever done that will know that they'll feel a lot of heat at the end. Therefore, not only are you changing the volume, but you're also changing the temperature. Here, they're saying the temperature remains the same. Big hint towards change the volume, see what happens to pressure. So here we've got a graph. Figure 4.2 shows how the pressure of the trapped gas depends on its volume. Now, as I pointed out in the lesson before, a lot of students think inverse proportion, let me just draw on this, looks something like, oops, my bad, let me go back in. Inverse proportion looks something like, so if that was my y-axis, there's my x. Let me just go to the next page. Well, I'll do it on the next page. They think it's a straight line like that. No, it's not. All right, inverse proportion is the shape that you are seeing in front of you right now. When the volume goes up, the pressure goes down. And then it says, describe the relationship shown by the graph between the pressure of the gas and the volume it occupies. Explain this relationship in terms of the molecules. Now, that's been very specific. So not only are they asking you to describe Boyle's law, they're asking you to explain how that relates to the molecules themselves. So if you imagine like this piston that I've got here, if I stick my thumb at the end and I try to push this all the way in, if you look at it, it pops straight back out. And the reason for that is gases are compressible. I'm trying to compress it, but when I let it go, the gas is pushing it straight back out. In other words, this piston can move backwards and forwards. All right? So what they're wanting here is for you to understand that P1 V1 equals P2 V2. In other words, P times V is a constant. You can write P1 V1 equals P2 V2. Tell the examiner, look, when the volume gets bigger, the molecules are more spread out and there are less frequent collisions. All right? So if you look at this, as the volume gets bigger, the pressure is going down. As the volume gets bigger, the molecules spread out. There are less frequent collisions, and therefore you've got a smaller pressure. If you wanted to flip that, you could say, look, as the volume decreases, pressure goes up because there's less space and there's more frequent collisions. You're welcome to flip it either way. It's not a big deal. Okay, so I hope that makes sense. Then it says, determine the volume occupied by the gas when it's released into the atmosphere at a pressure of 0.10 megapascals. You'll need data from 4.2. Well, this is where we need to come back here. And what the examiner's after is that you understand P times V is a constant. So let me try to pick a number that looks kind of nice and easy to look at. Let me find one. I'm zooming in here. Yep, okay. I'm going to come down here. And down here, 0.20 meters cubed. If I was to go all the way along, all right, that to me is spot on one. It's not well drawn there. It's 1 megapascals. So if I go across from 0. Now you could do this with any point, by the way. I'm just looking at one that gives me a nice number that isn't in between anywhere, and I need to use half boxes. I'm just looking, okay, 0.2, what do you give me? You give me 1 megapascal. So what do I need to do with that? Well, by using a calculator, you would do 1 times 0.2, which of course is 0.2. So what you've got, guys, is you've got, let me just do this, P1 V1 equals P2 V2, which effectively gives you 1 times 0.2 equals volume, pressure 2, which is 0.1, which is given us, times volume 2. And our job here is to find volume 2. And the way we would do that is we would do 1 times 0.2. I'll just do it here. 1 times 0.2 divided by 0.1. And guys, what you'll get is you'll get 2 meters cubed. Or that's what I think we should get. Yep. So don't worry what the mark scheme says. We're basically getting it's actually 2 meters cubed. And depending on whether you actually put in the megapascals or not, you could have ended up having 2 times 10 to the 5, but it is 2 meters cubed. I hope that makes sense. And it comes from P1 V1 equals P2 V2. Let me just get rid of this. Okay, next, an unused cylinder of the compressed gas is moved into a cold warehouse. The temperature of the gas decreases. State how the decrease in the temperature affects the motion of the gas molecules. Again, hopefully from the lesson we did previously, you'll understand, well, look, kinetic energy is related to temperature. So the smaller the temperature, the less kinetic energy the molecules have. In other words, they slow down. What about the pressure of the gas in the cylinder? Well, look, if they slow down, they have less kinetic energy. They're colliding less often, which means the pressure is going to go down. We okay with this, Pugs? Do you have any questions you want me to crack on? Brilliant. Okay. So next, question 4A from October-November 2016, paper 4, part 1. In an experiment, cold water is poured into a bowl made of an insulating material. The container is placed in a draft-free room. In other words, there's no wind or air conditioning. Windows are closed. After several hours, the volume and the temperature of the water are found to have decreased. Name and describe the process that causes the decrease in volume of water and explain why the temperature of the water decreases. Now, guys, this is a topic that I've not covered with you, but it is now going to mix in with gas laws. We are, of course, talking about evaporation. Look, a lot of students think evaporation happens only when water is boiling. If you're like me and you sleep with a glass of water, better still a bottle of water by your bedside, if you wake up in the morning, you will see condensation at the top of the bottle. You do not have underfloor heating. If you do, that's pretty cool, but most people don't. So why is there condensation at the top of the bottle? It's because the water's trying to evaporate. Water will evaporate at any temperature. Don't believe me? After this lesson, go and open the freezer and you'll see cold smoke, as my kids would call it, come out into your face. It's evaporated water, even from a freezer. All right? So, yes, when water is boiling, it's more noticeable. But even from a freezer, water will evaporate. And if you think about, guys, you've had a shower and you come out of the shower and you'll see steam in the walls. Trust me, you are not having a shower in boiling water. all right, because you'd be going straight to the hospital before you'd even finish that shower. So the point is, evaporation occurs at any temperature. It's more noticeable when things are boiling. So what happens in evaporation? The most energetic molecules have overcome the forces of attraction and they've left the surface of the liquid. So what does that mean? Well, think about it. You've got three states of matter: solid, liquid, gas. A liquid's turned into a gas. Gases have more energy. So if gas has more energy, what's left behind? A liquid with less energy. Guys, this is why when we play sports and we sweat, it cools us down. If it's a hot summer's day and you're playing football or wherever, you're playing sport and you throw water over yourself, it's to cool you down. But one of the main reasons it cools you down is not what you think. Yes, if you put very cold water over yourself, yes, it was cold to begin with. But what happens is heat from your body will evaporate that water. Now think about what happens. A liquid is just turned into a gas. Where did it get the energy from? Your body. Your body has given energy to the water. It's evaporated. So temporarily, at least, you're feeling cooler. Why do I say temporarily? If you're going to keep running around playing football, you're going to heat up. Or maybe as a kid, maybe this still happens, and you're embarrassed to admit it, but your mother, you've got a fever and your mother takes a cold towel and puts over your forehead. Why? Heat from your forehead, when you've got this high temperature, will evaporate the water in the towel. It will escape. The liquid is turned into a gas. More energy is gone and leaving less energy behind. So that's exactly what I've explained there. That's exactly what that answer says. Evaporation, highest energy molecules have escaped, leaving less energetic molecule behind. So the overall temperature of the remaining liquid decreases. I hope that makes sense. In a second experiment using the same apparatus and the same initial amount of cold water as in A, an electric fan blows air over the top of the bowl. So now you've got a draft. Predict and explain how the results of this experiment compare with the results of experiment A. Now, if you've ever had a coffee, Starbucks, Costa, whatever, okay, free shout out to Starbucks and Costa. Pugs, I hope they're paying you for this shout out, okay? If you've ever been to a coffee shop or hot chocolate, you know I love hot chocolate, and there's a lid on it, what do? If you really want to drink it quick, you take the lid off and you blow over it. No, there is no air conditioning coming out your mouth, okay? That doesn't happen. But what you're doing is any molecules that have evaporated, you're blowing them away so they cannot fall back inside. But guys, if you've ever been bored, okay, and okay, I've got a glass of water here, but let's just imagine that was a glass of a fizzy drink. Okay, I could give shout outs to fizzy drink, but pay ZNotes. But let's say it was a fizzy drink. If you ever look at the top of a fizzy drink, you'll see kind of gas molecules bounce up and then bounce back down. Okay, if you've ever been that bored, you'll see this happening. Now, that's visible to us. You can't see water molecules escape, all right? But if you've ever had a lid on top of a coffee and you take the lid off, you'll feel condensation on the inside. That was trying to escape. So the point is, the lid is there for that reason. If you try to blow that away now as it's popping up, what's happening is you're blowing the evaporated molecules away. Therefore, they cannot fall back inside and the whole thing becomes cooler. If you've ever been in humid weather, you'll know that's, well, in my opinion, in my humble opinion, that's the most horrible weather that there is because you feel sweaty and horrible. All right, because any moisture in the air, as your body's trying to cool down, it just sticks to you and it gives you that horrible feeling, unless, of course, you're on holiday and you don't care. Okay, so what happens in this experiment? Greater decrease in temperature in A. Why? Because the fan removes the vapor, it blows it away, it reduces the humidity, just like I've said. Therefore, there's more evaporation. If there's more evaporation, it's going to cool down a lot more. Pugs, any questions there, or are we good to keep going?
Let's crack on.
Cool. So next one, a third experiment, the same initial amount of cold water. Now look at all these experiments. They're treating it like we did gas laws. They're only changing one thing at a time. So same initial amount of cold water, okay, poured into a metal bowl this time. The metal bowl is the same size and shape as a bowl used in A. See that? They keep keeping everything the same, but this time they've only changed the fact that it's metal. One variable at a time, guys, okay? That's how we do experiments. Compared with experiment A, what can you tell me about the decrease in temperature? Okay, the decrease in temperature, sorry, is less than the same time. Explain why. Well, guys, this time, metal is a very good conductor. So what's going to happen here is heat is going to pass from the liquid or from the surroundings, raising the temperature. All right? So, like if the room is hotter, that heat is going to pass into the liquid, raising its temperature. That's why the decrease in temperature is less. So let me give you an analogy that I give students quite a lot. Let's say I asked you to dig a hole, right? You go to the beach, nice sunny day. I asked you to dig a hole 1 meter deep, 1 meter wide, 1 meter long. Now, I want you to imagine that to be like evaporation. So you're digging that hole, but unbeknown to you, I'm sweeping some of it, not all of it, back inside. Well, if I'm sweeping some of it back inside, what's happening there is, in the analogy, the temperature's going back up. So whilst the evaporation is trying to cool it down, the temperature is actually increasing again because heat is being gained from the surroundings from the metal container because it's a good conductor of thermal energy. All right. The only time that the water would lose energy to the room if the water was warmer than the room to begin with. But if the water's cold, it's going to gain heat. It's a common misconception. You know, when I teach students, you talk about latent heat and stuff, which is coming. I think, no, we've done that actually. And students will talk about ice creams and they'll go, why does it melt? Or, you know, why do we need to make sure the ice cream's insulated or something cold is insulated? And they'll say, to stop heat being lost to the surroundings. And I'll say, when's the last time you stood and put your hand above an ice cream to go, ah, that's so warm? Guys, cold things don't lose heat to the surroundings. Cold things gain heat from the surroundings. That's why the metal conductor here is decreasing how quickly it cools down because it's gaining energy. I hope that makes sense.
Yep.
Next, here's a Boyle's Law question, a common Boyle's Law question. Question 5A from February-March 2016, paper 4, variant 2. A student carries out an experiment to find the relationship between the pressure and the volume of a fixed mass of gas. The table contains 4 of her sets of measurements. Use the data in the table to suggest how the relationship between the pressure and the volume in this experiment. Explain how you reach your conclusion. Guys, a lot of students will look at this and go, well, I don't know what's happening. Pressure goes up, volume goes down. That's not what they're after. Remember, P times V is a constant. So what they want you to do is multiply 250 by 30, 500 times 15.2, 750 times 9.8, 1,000 times 7.6. And what you'll get is all the values are roughly speaking 7,500. In other words, P times V is a constant. Now, you might say, why did I just say roughly speaking? Because it's an experiment. You get errors. Things go up a bit, things go down a bit. But broadly speaking, if you were to plot the graph, it would be that curved graph, okay? The inverse proportion graph, not the straight line, but high pressure, low volume, low pressure, bigger volume, okay?
Can we revisit that for a second? Let's just show people how it looks.
Absolutely, absolutely. So there's the Boyle's Law graph right here. So what a lot of students think is the graph looks something like, oh, that's terrible. Let me do that again. What a lot of students think, guys, is that it's a straight line. I really should try to get a ruler for computers. I wonder if there is one. But let me just erase the top line. But in actual fact, it's a curved line. You okay with that, Pugs?
Yep.
Okay. So what they're talking about here in that table is exactly this. Okay, and when you multiply them together, just like we did in that first exam question, we multiplied 2 numbers together and then divided it by the new, I think it was pressure in that question to get a new volume. P times V is a constant. That's the whole point about Boyle's Law. So if the pressure doubles, the volume halves, or if the volume became a quarter, the pressure would be 4 times as much. All right, when you multiply them together, you're always going to get the same answer. okay? Or vice versa. I hope you understand what that means. I don't know if those chocolates still exist, okay? Where if you've got white chocolate on the outside, it was dark on the inside, and if you had
Yeah.
dark on the outside, it was light white chocolate on the inside, vice versa, okay? P times V is a constant. Okay, these are just all different ways of saying the exact same thing. State the property of the gas apart from the mass that remains constant during the experiment. You know, the examiner's been a bit naughty there, right? Because a lot of students would say mass, especially when I've taught them over a period of time. We go, look, guys, whatever's in that pump, we don't increase the gas. We just leave it the same. But what will remain the same in Boyle's law? Remember, we did it earlier. Temperature. We're only ever going to change one variable at a time. And then part B, slightly not fully related. A lake is 5 meters deep. The density is 1,000. Calculate the pressure at the bottom. Pressure equals density times gravity times height. So this is the pressure formula for a fluid. You've got the depth. You should know gravity is 10, and you know the density of water is 1,000. Plug in the numbers, and you get 50,000 pascals or 50 kilopascals. Okay. And then a bubble of gas escapes from the mud at the bottom of the lake and rises to the surface. Please tick one row in the table to indicate what happens to the volume, the mass, and the density of the bubble in the gas. So look, they're actually mixing density and, you know, knowledge about gas laws as well. So, you know, if this bubble is going to go to the top, you know, I don't know if you've ever tried talking underwater. The bubble, when it comes to the top, it gets bigger. In fact, I could be really crude here. And let's say you've lit off some methane gas in the bathtub. Not the best example. Probably a smelly example. Or in a swimming pool. When that bubble gets to the top, it expands. It gets bigger. So what's going to happen to the volume of the bubble? For sure, the volume is going to increase. All right. What's going to happen to the mass of the bubble? Well, look, the gas that comes out, the mass is going to stay the same. What's going to happen to the density? Well, this is slightly different from gas laws. But when volume increases, density decreases. Okay, so if I was to tick the boxes now, the volume of the bubble goes up. The mass of the gas stays the same because it's stuck in that bubble. The density goes down. Think of a hot air balloon, guys. Why does a hot air balloon rise? Because it's less dense than the air around about it. And when you heat it up, the balloon becomes bigger, so it becomes even less dense. And when things are less dense, they will always rise. Look up the topics of conduction, convection, and radiation, and also look up density equals mass over volume. So what you'll have saw there, guys, it's gas laws, but with a mixture of some other topics. And that just happens. That's the nature of exams. You're always going to get that. And if I'm not mistaken, that is all the questions.
Yep.
Bugs, do you have any questions to ask, or what do you want to do here?
Well, I guess we're started for the day. Let's wrap the session up. Thank you everyone for tuning in, and catch us again on next Tuesday. For updates, you can subscribe to the YouTube channel. Make sure you press the bell icon. Follow us on our Instagram page, and to ask us questions, join the ZNotes student community on Discord. Thank you. See you all then.
Thank you very much.